Good morning, everyone. Today, I'll be presenting our research on finite elemental analysis, simulating Ilizarov external fixator biomechanics. I have no conflict of interest to disclose. Introduction. The Ilizarov external fixator was first introduced by Ilizarov in 1951. Compared to more conventional monolateral external fixators, ring-type fixators were known to provide superior resistance to bending and torsional forces. Let me present a case study. A 20-year-old female patient suffered multiple injuries from a fall, including a gastrial type 3A open tibial fracture. We treated her using an Ilizarov external fixator combined with continuous local antibiotic perfusion therapy. After about 2 months of initial treatment, we successfully controlled the infection and we are waiting for bone healing. This arises an important question. How long should the external fixator remain in place? To address this, we decided to examine bone strength using finite element analysis. However, we encountered an interesting consideration. In Ilizarov external fixation, the wires are fixed under tension, which means the apparent material property should change. Our primary object was to investigate the apparent material properties of wires in Ilizarov external fixators. Method. We conducted our first experiment using 5 1.8 mm diameter smooth wires. We compared 3 different ring attachment conditions: without tension, with 19 kgf tension, with 130 kgf tension. We performed 3-point bending tests on each wire with the following parameters: support span 181 mm, central force application at 2 mm per minute. We recorded force displacement curve and force at 2 mm displacement. FEM model. We then created a finite element model of the mechanical test with these applications: mesh 0.1 to 1 mm tetrahedral elements, wire 1.8 mm diameter, 181 mm cylindrical, indenter 5 mm diameter cylinder, and fixation 5 mm cubes. For material properties, we used wire titanium array with various Young modulus values and Poisson ratio of 0.28, identer and end fixation stainless steel with Young modulus of 196 GPa and Poisson ratio of 0.34. Boundary condition. We set the following boundary condition: complete constraint of end fixations, 2 mm forces displacement of indenter in 200 steps, contact analysis between indenter and wire. Evaluation method. The force obtained from experiment 1 were compared with those generated in experiment 2 under various Young modulus values, allowing us to back calculate the apparent Young modulus of the wires. Result. Experiment 1. The force at 2 mm displacement was 8.19 N without tension, 40.4 N with 90 kgf tension, 56.5 N with 130 kgf tension. Using our approximation formula, we calculated the apparent Young modulus: 159 GPa for 8.19 N 786 GPa for 40.4 N, 1099 GPa for 56.5 N. Our next objective was to create a model considering these apparent material properties and evaluate stability difference based on varying material properties. We used CT scan from the patient's contralateral leg to create our model, which included bone model from CT, cartilage between bones, Ilizarov fixator with 4 rings, 4 bars, and 8 1.8 mm smooth pin, 10 mm defect in tibial shaft. We applied the following material properties: bone using Hayek conversion equation, cartilage, Young modules 10 MPa, Poisson ratio 0.49, rings and bars standard steel, smooth pin testing 3 Young module values, Poisson ratio 0.29, bone defect 1 Pa. Boundary condition. For this experiment, we set translational load 600 N axial pressure on femur, constraint complete teres fixation, contact analysis all smooth pin and tibia. Evaluation criteria. We evaluated the minimum principal strain in the bone defect area for all 3 smooth pin material properties. Result. Let me show you the simulation video for each model. As you can see, the 159 GPa model showed the largest deformation. We applied tension of 90 kgf or more to the wire. The overall model stiffness increased by approximately 30%. Discussion. Previous studies have modeled Ilizarov fixator wires in different ways: beam elements, truss elements, solid elements. Beam element with applied tension, FEM reproduction showed 10% higher than measured values. But beam element can't be set in mechanical finder. Truss element with applied tension results comparative to previous reports. Solid element with applied tension, compare beam and solid element. No significant behavior differences. Beam element more computationally efficient with sufficient accuracy. Conclusion. We successfully reproduce smooth wire behavior using apparent Young modules in mechanical finder. This method offered simply model creation compared to initial tension methods. Our result shows that 90 kgf and 130 kgf tension model demonstrate equivalent apparent stiffness. Thank you for your attention.